Welcome back. Now we're going to get into the biggie. Section 5.4 is the fundamental theorem of calculus. It's going to tell us we can compute area integrals and definite integrals by finding an antiderivative. So here's the first fundamental theorem of calculus. It's for continuous functions on a closed interval. It says then the definite integral of f from a to b is equal to the value of its antiderivative, capital F, evaluated at b minus the antiderivative evaluated at a. So to evaluate a definite integral, just find its antiderivative. At b and a and subtract. Okay, so here's some examples. We looked in the last section at finding the value of this integral by drawing the triangle described by the line y is equal to 6x. We cut it off from 3 to 5, so that makes it a trapezoid, right? Let me draw it right here. Y is equal to 6x is a pretty steep line. Say this is x is equal to 3, and this is x is equal to 5. When x is 3, 3 times 6 is 18. When x is 5, 6 times 5 is 30. So this thing is a trapezoid. So here we're going to compute this by geometry. That the area of a trapezoid is 1/2 base 1 plus base 2 times the height. Base 1 has height of 18. Base 2 has height of 30. And the height of the trapezoid, which is the distance between the parallel lines, in this example, is 2. So 18 plus 30 is 48. Half of 2 is 1. So this gives us an area of 48. Now let's use calculus. We find an antiderivative of 6x. So we integrate x and get x squared over 2. Half of 6 gives us 3. We don't need the plus c because it's going to subtract out. Now this bar tells us we're going to evaluate it at 5 and at 3. The 5 goes in first. 3 times 5 squared minus 3 times 3 squared. So the first bit is 25 times 3 is 75. 9 times 3 is 27. So let's see, 7 from 15 is 8. 2 from 6 is 4. By gosh, by golly, we got the 48 that we got using geometry. And that's because of the fundamental theorem of calculus. In the next example, we've got to start by rewriting 1 over the square root of x as x to the negative 1/2. Then we find the antiderivative. You got to add 1 to the exponent, divide by the new exponent. And so our antiderivative in this case is going to be x to the 1/2. When you divide by 1/2, you get a factor of 2 out here. And then you get the integral of x is 1/2 x squared to be evaluated from 1 to 4. So we have 2 times the square root of 4 plus 1/2 of 4 squared, that's the f of b, minus f of a, 2 times the square root of 1, plus 1/2 of 1 squared. So the square root of 4 is 2. 2 times 2 is 4. 4 squared is 16. Half of 16 is 8. Back here, 1 to any power is 1, so this is going to be 2 plus 1/2. So I have 4 plus 8 is 12, minus 2 is 10, minus 1/2 is 9.5. Okay, find an antiderivative, evaluate the endpoints, and that's how you use the fundamental theorem of calculus to compute a definite integral. In our next one, the 8 is a constant. We can pull it out. The antiderivative of secant squared, if you remember, is the tangent of x, because the derivative of tangent is secant squared. So I have to figure out what the tangent of pi over 4 is, and then the tangent of 0. Well, I know the tangent of 0 is 0. Tangent of pi over 4 is 1. So we get 8 out of that integral. Next page. Okay, now we don't have any formula to integrate the absolute value of x, so let me appeal to your understanding of the problem geometrically. The absolute value of x is a v-shaped graph, like this. So if I say that this is -3 and that this is +2, we're finding the area in here. So if you want to do this as an integral, then you've got to realize that the equation here is the line y is equal to x, but the equation back here is the line y is equal to -x. So I would have to break this up into two integrals. Along the line y is equal to -x, goes from -3 to 0. But then the line y is equal to x takes over from 0 to 2. Now we can use that fundamental theorem of calculus. When you integrate -x, you get -x squared over 2 from -3 to 0. And here you get a +x squared over 2 from 0 to 2. When x is 0, you get 0. When x is -3, you get 9/2. The negative goes in for x, it's squared, then divided by 2. Then you've got the minus sign. So you've got minus a minus. Now when you put the 2 in, you get 2 squared over 2, which is 4/2 minus 0. So you have 9/2 plus 4/2 is 13/2. If you use geometry, this is the ordered pair -3, 3, and this is the ordered pair 2, 2. So the triangle on the left has area 1/2 base times height. The triangle on the right has 1/2 base times height. So there's our 9/2 plus our 4/2 right there to give us the 13/2. Okay. All right, take a peek at the next one. Does anybody recognize the function whose derivative is 1 over the square root of 1 minus x squared? Well, I do. That's the arcsine of x. Then we have to evaluate that from 0 to 1/2. So we need the arcsine of 1/2 minus the arcsine of 0. The arcsine of 1/2 is the angle that we take the sine of to get 1/2. That's pi over 6. The angle that we take the sine of to get 0 is 0. So this integral has a value of pi over 6. Okay, so finally, example 6 wants us to find the area between the graph of the sine of x and the x-axis. So that's the first hump of the sine of x curve. And so we know now that that's a definite integral from 0 to pi of the sine of x dx. Remember that the antiderivative of the sine of x is minus the cosine of x. So we're going to have to compute minus the cosine of pi and then subtract minus the cosine of 0. Cosine of pi is -1. This becomes a plus. Cosine of 0 is 1. So there's 2 square units of area in there. Okay, so that's the first fundamental theorem of calculus. You compute a definite integral by finding an antiderivative. Then it's the antiderivative of the top limit minus the antiderivative of the bottom limit. And that number, if that function's a positive curve, can be interpreted as the area under the curve. Other applications are that if that function describes the velocity of an object, then its antiderivative gives you the total displacement of the object. Now, if there's a first fundamental theorem of calculus, by gosh, there's going to be a second fundamental theorem of calculus. And there is. If we replace the upper limit with the variable x and replace the dummy variable in the expression in the integrand with t, or whatever other variable, then the integral from a to x f of t dt defines a function of x. It's the antiderivative of f as a function of x. Since it's a function of x, and it's a continuous function of x because little f is continuous, then we can take its derivative. So we denote its derivative as capital F prime, or take the derivative of the integral. And what that does is it gives us the integrand as a function of x. Well, what does this say? This says that the operations of differentiation and integration are inverses of one another. They undo each other. The derivative of an integral is the integrand, just like the integral of a derivative is the integrand. Differentiation and integration are inverse operations. They cancel each other out when you act a derivative on an integral and when you act an integral on a derivative. They cancel each other out and you get the integrand back. That's just analogous to, say you have the square root of an expression and then you square it. Well, you get rid of the square root sign by squaring it. You get rid of an integral sign by taking its derivative. There's a chain rule version of the second fundamental theorem of calculus. If the upper limit is something other than a single x, if it's a function of x, then you apply the chain rule. The derivative kills the integral and gives you the integrand as a function of the upper limit, and then the chain rule part, you take the derivative of the upper limit. In both of these second fundamental theorems of calculus, the upper limit must be the variable expression. If it's not, you change the order of integration and put a minus sign on it. So here's two functions. F of x is the integral of 3t squared plus 9 over the cosine of t integrated from 2 to x. And g of x is the integral of the square root of the tangent of t integrated from 0 to x squared. And we want to find the derivatives of both those functions. And we can find the derivatives without finding the antiderivatives, which is a good thing because we don't know how to find the antiderivative of either one of those bad boys. But we do know that the derivative of capital F means I'm taking the derivative of the integral. So I'm going to write the derivative of capital F is the derivative of this integral. Then these operations cancel each other out, and we get a function of the upper limit. And so we're going to get 3x squared plus 9 divided by the cosine of x. There is no plus c on here. It's a derivative. The derivative of the constant is 0. Similarly, g prime of x is the derivative with respect to x of the integral from 0 to x squared of the square root of the tangent of t. So again, this operation and that operation cancels each other out. Those are gone, and we get the integrand as a function of the upper limit. So we're going to get the square root of the tangent of x squared. Now comes the chain rule. X squared is a function of x, we put its derivative right there. So that's the value of the integrand as a function of the upper limit times the derivative of the upper limit. And that is the second fundamental theorem of calculus. So those are the two big boys. Those are the two important things, and we get them right here in section 5.4. So get some practice in computing definite integrals. It's simply one more step beyond computing indefinite integrals, and that step just involves